11C, proportion and the golden ratio. The Greek said that the most good-looking division of the line looks like this. If I take a piece of the line, if I take a whole piece of the line and divide it into two pieces, divided by the longer side, and if I take the longer side and compare it with the shorter side, if I have the ratio of these two lines and the ratio of the whole line in a long piece, if I have the ratio of them being equal, which then look like this in the equation, if I try to solve for this, you'll notice that the ratio between the two is a nice number with a square root inside. This number is really close to 1.6 and it's really close to 8/5. This is called the golden ratio. Now, if I have a line and I know that I divided according to the golden ratio, let's use 1.62 as an approximation. If I know the length of the longer piece, how long should the whole line be? So we can do this two different ways. Personally, I only remember that the golden ratio is the ratio between the long and the short side. So in this case, I would say that the longer side is 5, the golden ratio is 1.62, and I can solve for L. L is 3.1. So that means the shorter side is 3.1. So together, the whole piece of line is 5 and 3.1 all together, right? So we have 5 on one side, 3.1 on the other, and together that's 8.1 centimeters. Now, next time when you're trying to decorate your Christmas tree or hang something from the ceiling, try to make sure that the length follows golden ratio and see if it looks nice. The Greeks not only used the golden ratio in lines, they also used it with rectangles with different shapes. A golden rectangle is a rectangle where the length and the width has the same ratio, has the same golden ratio. That's roughly equal to 1.62 or 8/5. It turns out that Parthenon the proportion of the Parthenon is closely matched with the golden rectangle. What we can do is we can look at some of our household items and we can see if any of them come close to the golden ratio. A standard letter size piece of paper that has a ratio of 1.29, 1.3. A picture frame, 8x10 picture frame, is about 1.25. And you'll notice that our HDTV or our computer monitor with a 16:9 ratio, that is closer to the golden ratio. Not exactly the same, it's a little bit wider, but it's closer. Golden rectangle is seen in nature. As it turns out, in nature, we'll have something that's growing outwards, right? We'll have something growing outwards. It could be a shell. It could be flowers. The flowers trying to get all crowded together and try to grow outwards. And typically, what will happen is it's slowly growing outwards at the same sort of radial speed. Okay, it's sort of expanding. The radius is getting bigger at the same rate. But the whole thing is spinning at the same time. It's sort of spinning like a clock. But as it spins and as the radius gets bigger, it turns out that we will have a logarithmic spiral. It looks really cool. We have a logarithmic spiral. And in the logarithmic spiral, it just so happened that the rectangle that we form are golden rectangles. And not only that, if I divide the rectangle into two parts, a square, the other part of the rectangle is also a golden rectangle. Another place where we can see something similar to the golden ratio is through the Fibonacci sequence. Fibonacci sequence is this. We take the previous two terms, say in this case 1 and 1, we add them up, and we find out the next term is 2. Then I can take the previous two terms, 1 and 2, I add them up, and I find that the next term is 3. I can add up the two terms, 2 and 3, to find that the next term is 5. Each of the next term, n plus 1, is equal to adding up the sum of the two previous terms, n and the one before, n minus 1. Fibonacci came up with the sequence when he was imagining rabbits growing in his head. Now, normal people would just actually grow rabbit as pets, but Fibonacci was imagining it. He was a mathematician. So what he imagined is this. His rabbit will take a month to grow into an adult. Whenever the rabbit grows into an adult, it will then give birth each of the subsequent months. The rabbit live forever and will make babies as long as they are an adult. So in the second month, the adult will give birth to a new baby rabbit. And in the third month, the rabbit will give birth to a new baby rabbit. And in the fourth month, another new baby rabbit. And on the fifth month, new baby rabbit. Now, the baby rabbit, any new baby rabbit that we have, will take a month to grow into an adult and then start making new babies. So suppose we have 5 rabbits right now. 5 rabbits in the fifth month. How do I know how many rabbits am I going to get in the next month? Well, it turns out we had to figure out how many of them are adults, right? And only adult rabbit will make babies, will increase our rabbit population. Now, if we look at the previous months, in the previous months, there are 3 rabbits. And these 3 rabbits are the only one that's going to grow into an adult. Or if they're not an adult, they will grow into an adult. The other 2 are new rabbits. They're baby rabbits. So we know that right now we have 5 rabbits, but since the previous months there were only 3 rabbits, we only have 3 adults, and we're going to make 3 new baby rabbits. So 5 plus 3 gives me 8. That's where Fibonacci sequence comes from. If we divide each of the Fibonacci terms with the previous term, you'll notice it also gets really, really close to the golden ratio. Very cool.